Look, we all know the pressure is on. Every project has a budget, and every budget feels like it's shrinking. When we're making things, especially in high volumes with injection molding, costs can spiral out of control before you even see the first part pop out. The price of good tool steel keeps creeping up, doesn't it? Then you get quoted a lead time that feels like an eternity. Time is money. That's a huge problem. But the really insidious costs, the ones that truly hurt your bottom line, are the hidden ones. Unexpected overruns, last-minute engineering changes, rework that nobody planned for. These financial hits aren't minor annoyances. They're genuine profit killers. They can turn a successful product launch into a struggle for survival. It's not about magic. It's about making smarter, more deliberate choices before you cut that first piece of steel, during that first cut, after that first cut. The secret isn't proprietary software or a miracle material. It's a mindset. Understand the entire process, from the first sketch on a napkin to the millionth part coming off the line. Over the next few minutes, we'll walk through practical, real-world ways to get a handle on molding costs. We'll break down where the money goes. Identify the key leverage points you can use. This isn't about cutting corners or making an inferior product. It's about being smarter, more efficient, and ultimately more profitable. Think of it as small fixes and thoughtful decisions that add up to massive savings. If 80% of the cost is baked in at the design stage, then that is where we have the most power. This is our biggest lever, design for manufacturability, or DFM. It's a fancy term for a simple idea. Design the part so it's easy to make. The single most effective thing you can do is to keep the part geometry as simple as possible. Every complex curve, every sharp internal corner, and every unnecessary feature adds hours of machining time and complexity to the mold build. Ask yourself, does this feature truly add value, or is it just a stylistic choice that's going to cost a fortune to produce? Simple, clean shapes are your best friend. Next, wage a war on undercuts. An undercut is any feature that prevents the part from being pulled straight out of the mold, like a side hole or a snap-fit latch. These features require complex, expensive mechanisms in the mold called side actions lifters. These moving parts dramatically increase the cost, complexity, and maintenance of the tool. Sometimes undercuts are unavoidable, but always challenge them. Can you achieve the same function with a clever design that eliminates the need for a side action? A simple pass-through core or a redesigned snap that can be bumped off can save you thousands of dollars in tooling and headaches down the road. Once you have a well-designed part, the next frontier for cost savings is the mold itself. This is where you make critical trade-offs between upfront tooling cost and long-term part cost. The first choice is the molds class, A class. 105 mold is a cheap, soft aluminum tool perfect for prototyping a few hundred parts. A-class 101 mold is made from the best hardened steel designed to run millions of cycles flawlessly. Don't pay for a million-cycle tool if you only need to make 50,000 parts. Pick the right class for your project's expected volume. This decision alone can cut your tooling bill in half if your volumes are modest. Another huge money saver is to lean on standardization. Your toolmaker can build a completely custom mold base or order a standard base from a supplier DME, Hasco, using a standard mold base and off-the-shelf components ejector pins, leader pins, bushings. Now let's talk about cavitation. This is the number of parts the mold makes in a single shot. A 2-cavity mold is cheaper to build, but the part cost will be much higher because you're only making 2 parts at a time. An 8-cavity mold has a higher upfront cost, but dramatically lowers the piece price. The key is to find the sweet spot. Balance your tooling budget against part volume and the size of the molding press available. Running a small 2-cavity mold in a giant 500-ton press is incredibly inefficient. Do the math to find the cavitation level that gives you the lowest total cost over the life of the project. Finally, think modular. You don't have to make the entire core and cavity out of one giant block of steel. For complex parts or parts that might need revisions, use modular inserts. Smaller, individual blocks of steel are inserted into the main mold base to form specific features. If a feature needs to be changed, remake that small, inexpensive insert instead of the entire multi-thousand-dollar cavity block. The plastic resin itself can account for a staggering 30 to 60% of your final part cost. This is a recurring cost that you will pay for every single part you make, so optimizing your material choice is non-negotiable. The number one rule is don't over-engineer it. It's tempting to choose a high-performance, space-age polymer just to be safe, but if a simple common polypropylene or ABS meets all of your functional requirements, using a pricey PEEK or Ultem is like making a lunchbox out of titanium. Work with your material supplier and molder to select the lowest cost resin that confidently checks all your boxes for strength, temperature resistance, chemical compatibility, UV stability. Next, consider the fillers. Adding glass fibers or carbon fibers to a resin can dramatically increase its strength and stiffness, but it's not a free lunch. Filled materials are more abrasive and cause faster wear on the mold, potentially leading to more frequent and costly maintenance. They can also be more difficult to process, sometimes requiring higher injection pressures and higher temperatures, which can impact cycle time. Unfilled resins are generally easier on the tool and can flow more readily into thin sections. Always question if a filled material is truly necessary, or if the same structural integrity can be achieved through better part design, like adding well-placed ribs. The global supply chain also offers opportunities for savings. An imported resin from overseas might have a lower per kilogram price, but you need to factor in shipping costs, import tariffs, and longer lead times. A longer lead time means you have to hold more inventory, which ties up cash. A local supplier might have a slightly higher material cost, but can offer just-in-time delivery, reducing your inventory burden and transportation fees. You have to do the total cost calculation. For some projects, a local source is the clear winner, while for others, the savings from an imported grade are worth the logistical complexity. Get quotes for both and make an informed decision. Lastly, let's talk about regrind and color. Regrind is recycled plastic from runners and scrap parts that is ground up and mixed back in with virgin material. Using a certain percentage of regrind can lead to significant material cost savings. However, it can affect the part's mechanical properties and appearance, so it's not suitable for all applications. Run tests to validate the maximum percentage of regrind your part can tolerate without compromising quality. Your color strategy matters too. Buying pre-colored resin is convenient but expensive. A cheaper and more flexible approach is to buy resin in its natural, uncolored state and mix in a color concentrate, called a master batch, at the press. This allows you to buy the base resin in bulk at a better price. In the world of injection molding, time is quite literally money. Every second you can shave off the cycle, time translates directly into lower part cost, higher factory output. Over a production run of hundreds of thousands of parts, saving just 2 seconds per cycle, saving 3 seconds per cycle, adds up to an enormous amount of money. The single biggest component of the cycle is cooling time. It can be 50% or more of the total cycle. This is the time it takes for the molten plastic to solidify enough to be ejected without deforming. Therefore, your number one focus for cycle time reduction should be on getting heat out of that mold as fast and as evenly as possible. This starts with the design of the cooling channels inside the mold. Don't just accept a few simple drilled lines. Push for an optimized cooling layout that places channels close to the hot spots of the part. For complex geometries, technologies like conformal cooling, where the channels follow the contour of the part, can slash cooling time dramatically. It costs more to build the mold this way, but the cycle time savings can pay for the investment many times over. The goal is to pull heat away uniformly to prevent warpage and allow you to open the mold sooner. A well-designed cooling circuit is a license to print money. The way plastic enters the part also has a huge impact. The design of the gate, where plastic enters the cavity, and the runner, the channel that feeds the gate, is critical. You also have a major choice to make between a hot runner and a cold runner system. A cold runner is just a channel in the mold that solidifies with the part and gets ejected as scrap, which can be reground. It's simple and cheap to build. A hot runner system has heated channels that keep the plastic molten all the way to the gate, so there is no runner scrap. Hot runners dramatically reduce material waste and can shorten cycle times, but they add significant cost and complexity to the mold. The decision is a classic trade-off. For high-volume production with expensive materials, a hot runner system is often the clear winner, despite its higher initial cost. For lower volumes or cheap materials, a cold runner is more economical. Be proactive, not reactive. Stop overpaying for molds. Stop overpaying for parts by understanding the system and making it work for you, not against you. Forget the fluff and the jargon. We're getting into the nuts and bolts, literally, of how to save real money. Let's get started. You can have the most brilliantly designed part and the most optimized mold, but without the right team and processes, you can still overpay. Your choice of supplier is paramount. Don't pick the lowest quote blindly. A low quote can be a warning sign. Cuts corners, inferior materials, lack of engineering depth. Look for a partner, not a vendor. Partner communicates clearly. Partner offers proactive suggestions. Partner invested in your success. They become an extension of your engineering team. Enter early supplier involvement, ESI. It's powerful and underutilized. Bring your molder and toolmaker in early. Share fluid CAD files. Let them run DFM and give feedback. They live and breathe this every day. They'll spot draft, wall thickness, undercuts you missed. Their early suggestions are almost free to implement and can save tens of thousands of dollars. And weeks of delays versus fixing after tool build. Manufacturing strategy affects cost. Where to build the tool. Build overseas to save on labor and steel. But weigh challenges. Communication across time zones and cultures, shipping logistics, difficulty making quick shop visits. Be militant about process control, hidden cost drivers, engineering change orders, poor documentation. Last-minute changes after tool build start are budget killers. Implement strict revision control. Poor documentation like lost CAD files, missing setup sheets, non-existent maintenance logs creates chaos. Every mold needs a complete dossier documenting its history. Changes in documentation aren't flashy like design or machining, but they're the bedrock of low-cost, low-stress production. Preventing cost through mold maintenance planning, wear-prone area design, first shot quality versus rework costs, long-term view. Cheap molds are often the most expensive. The earlier you act, the more powerful your actions are. We're going to build a mental toolkit that empowers you to challenge assumptions, ask the right questions, and guide your projects toward a healthier financial outcome. We'll break down practical, proven ways to cut costs before, during, and after tooling. Recap the 5 biggest cost levers. Design for manufacturability, smart mold design and standard components, cavitation versus machine size, material strategy, cycle time, and process efficiency. Most cost is locked in early, long before production starts. Cost reduction is systemic, not one decision. Review your part design. Involve your molder earlier. Audit your tooling strategy. Be proactive, not reactive.